What if you could go from design to injection molded parts in a week instead of months? Sounds impossible? Well, then check this out. That's right. With 3D printed mold inserts, you can quickly and cheaply manufacture your parts with injection molding. For today's webinar, we pulled from our experience making 3D printed mold inserts, which includes core injection molding design principles, molding simulation tools with SOLIDWORKS plastics, 3D printing material science, knowledge of 3D printing accuracy and precision, and using a desktop injection mold machine so that you too can be successful with this awesome application. Let's get started. To really demonstrate this application properly, I first had to come up with a valid scenario. And honestly, this took some effort because 3D printing has come a long way. So long that if you take away the one major benefit of injection molding, that is, extremely high production quantities, suddenly the overlap between injection molding and 3D printing becomes very large. Therefore, to come up with my idea, I not only had to rack my brain for a valid part, I also had to list out all the criteria that would rule out 3D printing full stop. Here's my mission statement. I work for a large-scale furniture manufacturer that's producing a new piece of cabinetry as part of a more refined product line. To avoid the stigma that it's just a plain, mass-produced bookshelf, every part of it needs to look finished and elegant, including these little shelf supports. So we need to redesign these and produce about 100 for the first batch of shelves that'll be used in load testing. But because this project is still in the early product development phase, we need to produce these cheaply. And we need them fast to get our product to market first before the other big box furniture manufacturers beat us to it. Okay, so we have our mission. Now, what's stopping me from just 3D printing these new shelf supports, since 3D printing can produce parts so rapidly and inexpensively? Well, because they will be used in load testing and for an aesthetics review, they need to be produced from white polypropylene to give us the most accurate one-to-one comparison, since it's the same material that'll be used in mass production. Polypropylene largely rules out FDM printing because it's so finicky to print with that filament availability is almost non-existent. The white color and smooth finish also rules out most SLS printers. Plus, the anisotropic nature of these two technologies means a load test could fail earlier than expected, contributing to unnecessary redesigns, despite the original mock-up potentially passing if made with a far more isotropic injection molding process. Speaking of isotropic, resin printing could be viable because it produces the most isotropic parts of the three main printing technologies. But the thermoset materials used here will not yield totally accurate test results to those produced from molded thermoplastic polypropylene parts. And since we need them quickly and inexpensively, that rules out CNC machining. So really, injection molding is our only option. With it, we can produce these shelf supports in the same material and process as we'll see in mass production. So it's a one-to-one comparison that'll yield the most accurately representative test results. But injection molding is not cheap, and it's not fast, as far as waiting a month or more for the tooling to be made and shipped over. And God forbid there's a design change and another mold set that must be machined, we'll be up a creek without a pickle. No wait, it's in a pickle or up a creek. Yeah, okay, that's how it goes. If only there was a way we could combine the benefits of both 3D printing and injection molding to get the parts and results we're after within a reasonable time frame and budget. Fortunately, there is a way. Using a Formlabs Form 4 series printer and their high-performance rigid 10K resin, you can actually 3D print your own injection molds in a fraction of the time and cost it would take to machine them. This is exactly what we did, so let's take a look at how we successfully pulled this off. Before starting my design, I first looked at the basic shelf support pegs from my office bookshelf to understand how they were molded and their design philosophy. You can see the draft angle here and the lack of a visible parting line, which suggests they hid the parting line along this face. To create an elegant gusset, I knew my shelf support design would need to be larger, so I designed mine to use 2 pegs instead of 1 that would interface with these holes in the side of the bookshelf. With these fundamentals in mind, this is what I modeled. It's really pretty basic, just 6 sketch-based features and 9 fillets. Since the mold halves will be here and here, pulling apart outwards like so, I added draft to all the necessary faces to avoid the part getting stuck in the mold. This was accomplished with a global variable set to 3.5 degrees because draft between 2 and 5 degrees is recommended for 3D printed mold inserts. Next, I needed to determine a gate location for optimal filling. SOLIDWORKS Plastics was indispensable for this. To set this up, I first chose fill as our simulation type because I'm new to injection mold design and I don't need all the advanced information these other types provide. For the injection material, I chose Novolin 1100H because it's a popular polypropylene according to those with more knowledge on this front than me. Within these injection settings, I set the injection pressure based on the desktop mold machine we purchased, and the mold temperature was set to ambient since we don't have any heating or cooling elements. The domain is the part itself, and for the boundary conditions, I opted for injection location, which is this sprue and gate I modeled up. Lastly, I created a curvature-based mesh with medium resolution to accurately capture the geometry and then ran the simulation. After testing a few different gate placements and analyzing time to fill for each, I finally ended up with this gate location. Here you can see the fill time is about the same at the 2 extremes. The air traps are located at sensible points. There aren't any extreme weld lines that could weaken the part or negatively impact its appearance. And the injection pressure is far less than the maximum for our machine. Happy with these results, I was ready to modify the design to incorporate 2 shelf supports in a single shot. For this, I rotated the part, added the runner and gate based on the ideal location from the simulation result, added the sprue and cold slug to fit the master unit die we'll be using. Then I modeled the runner to connect the sprue to the gate. And finally, mirrored and combined everything together. From here, I retested the simulation and the results still looked okay. Now there are 2 best practices I want to point out on this model that I learned from the great injection molding hobbyist and software legend, John Sacha Lealoha. First, the combined cross-sectional area of these 2 runners should be equivalent to that of the sprue. Second, a cold slug, like you see here, is needed to trap the slightly cooler plastic exiting the mold machine so that it doesn't foul your shot. I also took some advice from John to initially size my gate to be about 1.8 millimeters square. I definitely couldn't have done this without his wealth of information, so I highly recommend you check out his channel, John SL Random Products. Now for me to know my injection pressure, sprue diameter, and mold size, I had to already know which desktop injection mold machine I would be using. After careful research, I decided on the Buster Beagle Mark III, a pneumatically powered kit you assemble for about $1,000. It's pretty basic to assemble and has good documentation for the BOM and manual. Plus, the frame, pneumatic cylinder, and all the electronics can be purchased from 2 separate lots, which makes it pretty easy to acquire everything at a reasonable cost. Here's a short montage of the assembly process.
Shall we begin? Let's begin now. Let's begin now.
Oh, for sure.
While all of this was going on, I was test printing pre-supplied mold insert files in Rigid 10K on our Form 4 to determine the dimensions needed for them to properly fit in the aluminum machined mold frame, or mud box, also supplied by Buster Beagle. The STL and step files that I tried from their Thingiverse page were too big for this mud box, so I guess the machining process changed a bit and the dimensions are now smaller than the originally modeled inserts. So, like the big purple man said,
Fine. I'll do it myself.
I modeled up this blank insert and set all the dimensions to be 0.1 millimeters undersized compared to the measured dimensions of the inside of the aluminum frame. I also scanned 1/2 of the mud box on both sides in our Brother laser printer and uploaded those images as sketch pictures to keep myself honest and accurate with my design. Lastly, I exaggerated the fillets to avoid any binding here. After printing it, it required some sanding to fit it into the frame because almost all the dimensions were about 0.2 millimeters oversized. So before I printed it for the final time, I modified the design to be about 0.2 millimeters smaller than I originally planned. This is a very common practice in 3D printing because while 3D printing may not exactly match what you model initially, once you know the discrepancy, you can modify the design to offset this discrepancy and get repeatable results within 0.05 millimeters or less from print to print. If you want a deeper explanation on this, check out our webinar, 3D Printing Tolerances Explained. Now that I had a mold insert blank that I could rely on, I added this part to my shelf support file. I can then add my air vents based on the location of the air traps in my simulation results. These are cut into 1/2 of the mold by 0.15 millimeters to allow air to pass, but not any plastic. To avoid wasting too much resin, I cut cavities into the back of the mold halves only where no plastic was being ejected to avoid weakening the mold. With the other half created, I was now ready to begin slicing and printing. In Preform, Formlabs Slicer, I set up my job for printing on our Form 4 in Rigid 10K at a layer height of 0.05 millimeters to really maximize a smooth finish and accuracy. Rigid 10K, a glass-filled resin, is one of Formlabs' highest performing materials and is the optimal resin for this application. It is capable of surviving the high temperatures of molten slag as weld fixtures and the extreme pressures of injection molding as mold inserts. For the best print orientation, my research concluded with mixed opinions. Some say print it straight on the build platform with the interface facing up. Others say print it on its side with the interface perpendicular to the plane of the build platform. However, I had great results printing it at a 30-degree angle across the X and Y axes. This maximizes flatness, minimizes peel forces, avoids distortion, and allows for easy removal of the molds from the static build platform without needing the build platform flex,
which we don't have.
Preform's auto-generated supports work extremely well for establishing the main structure that links the part to the build platform, and 9 times out of 10 are perfect as is. But for parts that need that extra level of accuracy, I go back in with manual supports to really cover all of my corners. Literally. With this 10.5-hour print kicked off at the end of the day, I could come in the next morning to a fully finished, beautiful looking print job that was ready for post-processing. Now, removing rigid 10K parts from the static build platform can be a bit tricky, but here's a useful tip. Use a pair of flush cutters, like the ones in the finish kit, as demonstrated here, to lift a small corner of the raft from the platform. Then you can slide the scraper under the raft and slowly peel the rest of it off. This is key because rigid 10K does not flex, instead just chipping and shattering, making removal very difficult if you approach it in a more ham-fisted way. I then washed both mold halves in a slightly dirty isopropyl alcohol bath for a few minutes to remove the majority of the resin. I then dumped this dirty resin into our wash L, which we haven't been using much for washing recently since we haven't been printing huge resin parts. I then refilled our bucket with fresh 99% IPA and finished washing any remaining resin from our 2 molds. Lastly, I gave each one a final hose down with fresh alcohol to remove any stubborn residue in the small recesses, and then left them to dry under a box fan. After about 30 minutes of drying, I placed them into our Cure V2, which blasts the part with heat at 80 degrees centigrade for 3 minutes, and then UV light for 7 minutes. I then like to let them cool down inside the cure to about 35 degrees centigrade before pulling them out to avoid any thermal shock. I check the temperature during cool down by starting up the cure and then aborting the cycle immediately after. Here you can see it reads 32 degrees. From here, it's just a matter of clipping off the supports, which is super easy to do with rigid 10K because the supports fly off so easily after curing. Once you get all the ones on the perimeter, you can then just twist and pull and the rest will crack off super easily. Then I clip off the taller support pips that are left and give it a good sanding with 120 grit on the corner that was the closest to the build platform, as well as the back face. Compared to FDM parts, resin parts are an absolute dream to sand, so I actually don't mind it too much. I had to go through a couple bouts of careful sanding to get the insert flush with the aluminum interface, but once there, it was time to heat up the Buster Beagle Mark III. Meanwhile, I took the mold halves outside and gave it a hit with some mold release spray, just in case. This was just to be safe, but likely was overkill with hindsight. If you want to go tighter with your draft, say 1.5 or 2 degrees, then some mold release might do you good. Back to the machine, the white polypropylene pellets we are using are from LNS Technologies, another desktop injection mold machine manufacturer. Their pellets come in nice 500cc containers and are only $10 each, so I went ahead and bought some ABS, HDPE, HIPS, and TPE 59A for future use. Hint, hint. Now, I will say this machine takes some dialing in because our first few shots weren't brilliant. It was either full stop or full go, winding up with either short shots or completely blown out fills.
Jesus Christ. Why is it doing that?
There were a number of variables that contributed to these conditions, but melt temperature, clamp setup, mold temperature, and piston ram speed were definitely prime factors. We played with the temperature, varying it between 220 Celsius all the way up to 245 Celsius, where we found good results at higher temperatures. Waiting different durations after refilling the chamber with pellets, the longer the better. Reducing the speed of the ram going down and up. Slower was better because too fast resulted in overfilled molds and suction. Varying the ratio of recycled plastic to fresh pellets inside the chamber, We don't have a grinder, so recycled plastic melted much slower, plus more fresh pellets performed smoother fills. Increasing the size of the gate, which we did with this round conical file, changing the hold and pack times. For this mold, a hold of about 10 seconds worked best, as well as heating up the mold prior to injecting using a blow dryer, which definitely helped reduce short shots substantially. Once we got it dialed in for this part, we did get plenty of good shots, which was a huge win. Still, some flashing was present, but if we had a milling machine, we could get this perfectly flat, and that would help immensely to reduce flashing. We got them cleaned up anyway, and installing them was a breeze. Here they are on our new luxury shelving product. They hold up loads really well, so I think we found our solution. Well, that's all from me for this one. As always, I learned a lot about mold design and have a new appreciation for folks in this industry, as well as how easy 3D printing is in comparison. There will be plenty of future videos on this topic, considering how much more material we have left to inject, incorporating SOLIDWORKS mold design and tools, building molds with a slide feature, and using SOLIDWORKS CAM for machining aluminum molds and mud boxes. I hope you all enjoyed this and gained a benefit from the knowledge here and from future videos in this series. Bye for now.